programmable logic controller, also known as a PLC, with a 24 volts direct current power supply and appropriate input and output modules, represents a suitable controller option. This system can solve the problem of driving 3-panel boards with 3 different contactors based on temperature and time, while ensuring that only 2 panels are active at any given time and providing the necessary accuracy for 20-minute cycles. Firstly, consider the PLC configuration. You will need an input module to connect a temperature sensor and start or stop signal, and an output module to control contactors A, B, and C. The PLC built-in timer functions can be used to control the 20-minute cycle. Next, think about the operational sequence. When the temperature is 20 degrees Fahrenheit or below, the PLC will energize the contactors for panels A and B for 20 minutes. After 20 minutes, the PLC will energize the contactor for panel A and energize the contactor for panel C. Following another 20 minutes, the PLC will energize the contactor for panel B and energize the contactor for panel A. This cycle will repeat indefinitely. To prevent the simultaneous energization of all 3 panels, the PLC can employ an interlock function. This function disables the contactor for a panel if another contactor is already energized, ensuring that only 2 panels operate at the same time. The PLC and its input-output modules must be housed in an outdoor enclosure rated for the appropriate weather conditions. Specific PLC recommendations include the Allen Bradley Micrologix 1100 or 1400 series, the Siemens S7-1200 series, and the Schneider Electric Modican N221 series. Consider additional features for your PLC setup. Remote monitoring can be achieved by equipping the PLC with an Ethernet or wireless module, allowing for remote monitoring and control. Data logging is another valuable feature, enabling the PLC to record temperature and other relevant data for troubleshooting and maintenance purposes. Fault detection can also be implemented. The PLC can detect faults in the temperature sensor or contactor circuit and alert maintenance personnel. The PLC programming language, typically ladder logic, allows for the creation of the control logic needed to implement the described sequence. Ladder logic uses a graphical representation of electrical circuits, making it relatively easy to understand and modify. The program must be designed to read the temperature sensor input, activate and deactivate the contactor outputs based on the timer settings, and implement the interlock function to prevent simultaneous energization of all 3 panels. The temperature sensor should be selected based on its accuracy, range, and suitability for outdoor use. A thermistor, a resistance temperature detector, or thermocouple could be used depending on the temperature range and accuracy requirements. Ensure the sensor is properly calibrated and shielded from direct sunlight to avoid inaccurate readings. The input module should be compatible with the chosen temperature sensor's output signal. The output module should be capable of handling the voltage and current requirements of the contactor coils. Relay outputs are commonly used for controlling contactors. The contactors should be selected based on their ability to handle the load current of the panels they control. They should also be rated for the appropriate voltage and duty cycle. Consider using definite purpose contactors, which are specifically designed for HVAC and other motor control applications. The outdoor enclosure should be chosen based on its NEMA rating. A NEMA 4 or 4X enclosure is suitable for outdoor use, as it provides protection against rain, snow, and ice. The enclosure should also be large enough to accommodate the PLC, input-output modules, power supply, and any other necessary component. Proper wiring practices are essential for ensuring the reliability and safety of the control system. Use appropriately sized conductors for all wiring connections and ensure that all connections are tight and secure. Follow the National Electrical Code (NEC) requirements for wiring methods, overcurrent protection, and grounding. In accordance with the 2014 NEC, refer to Article 310.15 for ampacity of conductors. Also, refer to Article 430 for motor circuits. Grounding is crucial for protecting against electrical shock and preventing equipment damage. The PLC, enclosure, and all other metal components should be properly grounded to a common grounding point. Refer to NEC Article 250 for grounding requirements. Overcurrent protection should be provided for the PLC input-output modules and contactor circuits. Fuses or circuit breakers should be sized according to the equipment's ratings and the NEC requirements. Surge protection should be installed to protect the PLC and other electronic components from voltage surges caused by lightning or other electrical disturbances. A surge protective device, SPD, should be installed at the main power entrance to the enclosure. Regularly inspect the control system to ensure that all components are functioning properly. Check the temperature sensor for accuracy, the contactors for proper operation, and the wiring connections for tightness. Clean the enclosure regularly to prevent the accumulation of dirt and debris. Periodically test the surge protection device to ensure that it is still functioning properly. If the PLC has remote monitoring capabilities, use this feature to monitor the system's performance and identify any potential problems. Review data logs for unusual temperature fluctuations or contactor cycling patterns, which may indicate a problem with the system. Be aware of safety considerations when working with electrical equipment. Always disconnect power before working on the control system. Use appropriate personal protective equipment, PPE, such as safety glasses and gloves. Follow lockout-tagout procedures to prevent accidental energization of the equipment while it is being serviced. The PLC program should be thoroughly tested before being put into service. Simulate different temperature conditions and timing sequences to verify that the control system is operating correctly. Use a multimeter to check the voltage and current levels at various points in the circuit. Monitor the temperature sensor readings and the contactor status to ensure that they are consistent with the expected behavior. The PLC program should be well documented, including a description of the control logic, input-output assignments, and timer settings. This documentation will be helpful for troubleshooting and maintenance purposes. The documentation should be stored in a safe and accessible location. Consider using a version control system to track changes to the PLC program. This will allow you to easily revert to previous versions if necessary. Proper commissioning is essential for ensuring that the control system is operating correctly. Verify that all wiring connections are tight and secure. Check the temperature sensor calibration. Test the contactor operation. Verify the timing sequences. Monitor the system's performance over a period of time to ensure that it is stable and reliable. The PLC can be programmed to provide additional features such as alarm notifications. For example, an alarm can be triggered if the temperature exceeds a certain threshold or if a contactor fails to operate. These alarms can be sent to maintenance personnel via email or text message. Consider implementing a human-machine interface (HMI) to provide a user-friendly interface for monitoring and controlling the system. The HMI can display temperature readings, contactor status, and other relevant information. It can also allow operators to manually override the control system if necessary. The PLC can be integrated with other building automation systems such as lighting control or HVAC systems. This integration can provide a more comprehensive control solution and improve energy efficiency. Consider using a standard communication protocol such as BACnet or Modbus to facilitate communication between the PLC and other systems. The PLC can be used to implement advanced control strategies such as proportional integral derivative (PID) control. PID control can be used to optimize the temperature control and minimize energy consumption. The specific parameters of the PID controller should be tuned to match the characteristics of the system. The PLC can be used to collect data on the system's performance over time. This data can be used to identify trends, optimize the control strategy, and improve the system's overall efficiency. The data can be stored in a database or spreadsheet for analysis. The PLC can be used to implement energy-saving strategies such as night setback or demand response. Night setback reduces the temperature setting during unoccupied hours to save energy. Demand response reduces the load on the electrical grid during peak demand periods. Proper maintenance is essential for ensuring the long-term reliability of the control system. Regularly inspect all components for wear and tear. Replace any worn or damaged components promptly. Clean the enclosure regularly to prevent the accumulation of dirt and debris. Calibrate the temperature sensor periodically to ensure its accuracy. Test the surge protection device annually. The PLC program should be backed up regularly to prevent data loss in the event of a hardware failure. The backup should be stored in a safe and accessible location. Consider using a cloud-based backup solution to protect against data loss due to fire, theft, or other disasters. The PLC should be protected from unauthorized access. Use strong passwords to prevent unauthorized users from accessing the PLC program or modifying its settings. Consider implementing a firewall to protect the PLC from network-based attacks. The PLC should be installed in a location that is protected from physical damage. Avoid installing the PLC in areas where it is exposed to excessive heat, moisture, or vibration. Consider using a vibration isolation mat to protect the PLC from vibration. The PLC should be installed in a location that is easily accessible for maintenance purposes. The location should be well lit and provide adequate space for working on the PLC. The PLC should be installed in accordance with all applicable codes and regulations. Consult with a qualified electrician to ensure that the installation is safe and code compliant. The selection of a PLC for this application requires careful consideration of several factors, including the number of input and output points required, the processing speed, the memory capacity, the communication capabilities, and the environmental conditions. The number of input and output points required will depend on the number of sensors and actuators that need to be connected to the PLC. In this case, there is at least one temperature sensor and 3 contactors that need to be controlled. The processing speed of the PLC will affect how quickly it can respond to changes in the input signals. The memory capacity of the PLC will determine how much program code and data can be stored in the PLC. The communication capabilities of the PLC will determine how it can communicate with other devices, such as HMI or other PLC. The environmental conditions, such as temperature, humidity, and vibration, will affect the reliability of the PLC.